Alright, welcome back everybody. In this video we're going to look at examples 3 through 5 from the Revisiting Area lesson. We'll start here with example 3. Find the area of the region bounded by the curve y equals x cubed minus 2x squared minus 5x plus 6, and the x-axis between x equals negative 2 and x equals 3 analytically. So we're going to find our definite integral values by hand here in this example. To help us get started, let's take a look at what this graph looks like between x equals negative 2 and x equals 3. So we'll go ahead and type that function in. We've got x to the third minus 2x squared minus 5x plus 6. And since we're only interested in finding the area between the curve and the axis from negative 2 to 3, I'm going to go in here and change my window so that I'm only looking at it from negative 2 to 3. There's what the graph of that looks like. And you can see that some of the region is above the axis and some of the region is below the axis. And we're interested in where that changes from above the axis to below the axis. And we can quickly confirm it looks like it happens at 0, or pardon me, at x equals 1. But we'll go ahead and find that 0 just to be sure. Like 99.9% sure that that's happening at 1. Yeah, it does happen at 1. So what we want to do in order to find the area of this region is we're going to integrate the function from negative 2 to 1. And we're going to integrate it from 1 to 3. And we're going to subtract away the integral that we get from 1 to 3. So we've got the integral from negative 2 to 1 of the function. And we're going to subtract away the integral from 1 to 3 of the function. Now actually finding this analytically won't be too terrible for us because we get the same antiderivative because we're using the same integrand. So we go ahead and find the antiderivative. It's going to be 1/4 x to the 4th. Minus 2/3 x to the 3rd minus 5/2 x squared plus 6x, which we're going to evaluate from negative 2 to 1. And then same antiderivative. Which we're going to evaluate from 1 to 3. Alright, and the calculation is going to be the hardest part here. We put 1 in for x, and that's going to give us 1/4 minus 2/3 minus 5/2 plus 6 minus, and then we put negative 2 in there. Let's see, that's 16 over 4, which is 4. Minus 2/3 times negative 8, so that's plus 16/3. Minus 5/2 times 4, so that's going to be minus 10. And minus 12. And then we're going to subtract away, and we'll get what we get when we substitute 3 in there. That's going to be 3 to the 4th is 81 over 4. Minus 2/3 times 27, which is just going to be minus 18. Minus 5/2 times 9, which is going to be minus 45 over 2. And plus 6 times 3, which is 18. Minus what we get when we evaluate it at 1, which we already did. That's 1/4 minus 2/3 minus 5/2 plus 6. And so we've got some calculation on our plate here now. Alright, so 1/4 minus 2/3 minus 5/2 plus 6. We change that to twelfths. It's 3/12 minus 8/12. That's negative 5/12 minus 30/12. So negative 35/12 plus 6. That's going to be 37/12 minus, And let's see what we get here. We've got negative 22 plus 4, that's negative 18. And that's negative 38 thirds. Alright. Let's see, 81 fourths and 45 halves. That's going to be 90 fourths. So negative 9 fourths minus 37 twelfths. Like I said, the calculation here is the worst part. Let's see, if I combine these together, that's 120, 152 twelfths. So we've got 189 twelfths minus, and that's going to be 327, negative 64 twelfths. And assuming all my calculations have been correct along the line here, and I didn't make a silly multiplication error, we end up with our final area of the region being 253 over 12, or for those of you who like the decimals, 21.083. Repeating. Alright. Now let me check myself here. This is outside the context of the problem, but I just want to check myself. I'm going to integrate the absolute value of this function over the interval. Absolute value of x to the third minus 2x squared minus 5x plus 6 with respect to x from negative 2 to 3. Let's see how my calculator does with this. And hopefully I get 21.083 repeating. Otherwise I did make a calculation mistake along the way here. Crossing my fingers pretty hard right now. Hey, alright, 21.083. Alright, good. My calculations were solid. Alright, let's go ahead and move on to examples 4 and 5. Example 4. We're supposed to find the area of the shaded region in the diagram below using analytical methods. Well, notice what we've got in our shaded region. We've got one region that's bounded by above by the line y equals negative 1/2 x plus 4, and the other region that's bounded above by the parabola. And so, in order to find the area here, we're going to take the integral from 0 to 4 of negative 1/2 x plus 4, and we're going to add to that the integral from 4 to 7 of x squared minus 10x plus 26. And I'm supposed to do this analytically, so I'm going to go ahead and find these antiderivatives by hand. And the calculation here is going to get a little bit ugly for us. Let's see, I've got negative 1/4 times 16, that's negative 4 plus 16 minus 0 plus 0 plus, oh boy, 343 over 3 minus 5 times 49, that's 245, plus 26 times 7, which is 182, minus 64 thirds, minus 80, plus 104. Alright, and for time-saving purposes, I'm going to go ahead and calculate this on my calculator. I've got negative 4 plus 16 plus 343 over 3 minus 245 plus 182 minus 64 thirds plus 80 minus 104. And we get 18 for the area of this region. Alright? So when we have a region bounded by two different curves above, we're just going to break it apart into those two separate curves and set up our limits of integration based off of those. Alright, example 5. Find the area of the shaded region in the diagram below using analytical methods. Well, in this one what I'm going to do, I can find the area underneath this curve by integrating the square root of x over the entire interval. Okay? And that'll give me the area that I've just shaded in blue. So to get the actual shaded region, I'm going to take the area of this whole rectangle minus the area of what's shaded in blue. So we've got a rectangle with a length and width of 3 and 9. So we're going to take 3 times 9 minus the integral from 0 to 9 of the square root of x. So we've got 27 minus, and the antiderivative of this is going to be 2/3 x to the 3/2, which we're going to evaluate from 0 to 9. We've got 27 minus, and let's see, x to the 3/2, if x is 9, that's going to be 27. 2 times 27 over 3 is going to be 18. And so we end up with 27 minus 18. And that gives us 9 for the area of the shaded region in this diagram. So we have to be adaptable when we're finding these areas of shaded regions, use things that we know about geometry, as well as what we know about how to find areas under curves using integrals, and tailor our approach to what we see pictorially or what we see graphically, and develop an appropriate model to come up with those calculations. And once we do that, then it's simply a matter of using the fundamental theorem of calculus part 2 to evaluate the integrals. Alright, that's the end of this video. See you guys next time. Have a great rest of your day.